हम्म, वीडियो बंद है।
Dr. Venugopal, would you like to try and share your slides just to check that the sharing mechanism works? Yeah, that seems to work. That's not in full screen mode at the moment. So if you could just try full screen. Thank you, that's brilliant. Yeah, you can stop sharing now. Yeah, it's a little tricky to stop the sharing, I've found. The other people, yeah, but excellent, thank you. I just wonder if that's everyone who's tested so far. Is Dr. Kulkarni online yet?
Yeah. So yes. So hall B. This is the hall B.
Yes. Hello.
Yes. So we are ready. This we can you start?
Well, I think we're waiting for Dr. Kulkarni. Is he here talking about the hydraulic jump?
Yeah. He's not in the list. He has not yet joined.
Yeah, maybe just wait another couple of minutes. Certainly, I want to hear that talk very much because it sounds very relevant to the food number work for the Western Ghats that I talked about yesterday. So the idea of a hydraulic jump sounds very interesting to me.
Yeah.
Perhaps Dr. Patanaik is checking where Dr. Kulkarni is. Yes, looking at pictures. Yeah. I think you'll be okay, Ambrosio. I'm sure the first two talks won't take too long. Because we'll get started in a moment. Does the IMD admin, do you know where Dr. Kulkarni is, or if there is a pre-recorded video, for example?
So how many are there in this session, Dr. Andy?
In the WebEx session, there are 10 participants.
No, all 6 participants are there, but the paper.
No, no, I can't see where Dr. Kulkarni is for first talk.
One talk, just a minute. I think I had the list. Anyway, once we start, they will come to know. Okay, so let us start it now. It is 7:40 locally. So yeah, may I now invite Dr. Andy Turner. So he is now well known. Today morning he was giving he has given a very interesting talk. Also appreciated by Dr. Krishnan and everything, and a very familiar face in the climate change, monsoon, and monsoon variability and projection. So yeah, and I'm not taking much time, so people are very much aware of him. So it is over to you, Andy Turner, to please start the proceedings.
Okay, thank you very much, Dr. Patanaik. It was good to see your talk just now in Hall A. I don't believe I can see Dr. Kulkarni for the first talk of the session. So I suggest that we, given that it's around about 10 past the hour or 20 to the hour in India, I suggest that we start with talk number 2. And if Dr. Kulkarni turns up, we put his talk in later. So Kieran, are you ready to be able to speak about interactions between depressions and Western disturbances?
Yeah.
Excellent, thank you. And for all speakers, you have 10 minutes, and I will give you a warning at 8 minutes so that you're aware that your time is running out. Okay, but please go ahead. when you like.
Okay, great. So this is the first of 2 talks that I'm giving, sandwiching Ambrogio in the middle. This is work we did on the IMPROVE project, and the kind of overarching aim of that project was looking at the causes of extreme or heavy rainfall over orography in India during and around the monsoon. So the first talk is looking at how interactions between tropical depressions or low pressure systems.
Excuse me, sorry for interrupting. Your presentation is not shared. Please put your presentation.
Share the screen, Kieran.
It is shared, isn't it?
No.
If you want, we can share from our end.
Oh, I got it. I just. Hang on with me. Oh, I didn't double.
There we are.
There we go. I think I didn't double click before.
Yeah.
Okay, fine.
And then just full screen it, please.
Yeah. Okay. So you can see the full screen version now.
Yes.
Okay, good. Sorry about that. Yeah, so this is looking at how interactions between tropical depressions or monsoon low pressure systems and western disturbances, which are a type of extratropical system, can result in those kinds of extreme orographic precipitation in the South Asian region. So I'll start with a very, very brief overview of what western disturbances are, because I know most people will be familiar with tropical depressions, but not everyone knows necessarily how western disturbance works. So they're these sort of extratropical-like systems. They inhabit the upper troposphere and they sit in the subtropical jet, and usually, but not entirely, affect North India during the winter. They can hit any part of India, any part of the year. And they're associated primarily with this region of big ascent ahead of them, this big ageostrophic ascent, and also with some forced ascent as flux associated with them strikes the mountains. So that's western disturbances, a quick revision. But onto the crux of this. So the motivation behind this work of understanding these interactions comes from the 2013 Uttarakhand floods primarily. So this is a very, very well studied event, and the general outcome of all that research is that the floods came about as a result of a western disturbance, which you can see here as a trough in the upper level. This reaches North India at exactly the same time. That's a low pressure system, which you can see here, a monsoon low pressure system moves northwestward into the same region. And the two reach Uttarakhand at a similar time, and that results in this extraordinary amount of rainfall over a large area that was very devastating. So that's the motivation. But that's just one case, and we want to look at as many as we can. So we have databases of tropical depressions or low pressure systems. You can see an example of the tracks up here. And then underneath that, we have western disturbances. So we also have a track catalogue of western disturbances from previous research. And all I've done here is simply to say, well, if 2 of them are present, if 1 each is present over India at the same time, then we say an interaction is happening. But that's a very loose definition of interaction, because they could be very far apart, or one or other could be quite weak. And so we restrict that a little bit for this study and say that only if they're very close, so in the left-hand side of this density plot, and if both systems are quite strong, so in the top half of this density plot, and we restrict these cases to this quadrant of the plot. And that gives us about 60 cases to look at. So having produced this, I then printed out synoptic charts for all 60 cases, all 59 cases, and moisture trajectory analyses, and vortex budgets, and all vorticity budgets, and all manner of academic weaponry was pointed at this. And eventually I concluded that there were 4 different types of interaction with some variance. But given the length of this talk, I'll just go through a particularly enlightening case study, or an illustrative case study from each of those interaction types. So the first type of interaction, the first way in which these can interact is a dynamical type of interaction. And quite simply, it's a vortex merger. So the 2 systems can merge with each other. When you think about it, a western disturbance is in the upper troposphere. This is this magenta blob here, and a low pressure system is in the lower troposphere primarily. So that's the orange blob here, and the 2 can sit on top of each other and superpose as PV anomalies can. And you can see that when that happens here, so what I've done is plotted vorticity ice lines at every 50 hectopascals through the troposphere. You can see a distinct entity is the low pressure system, a distinct entity of the trough of the westerner disturbance. As they come together, they start to interact in the mid-levels and then form this single, slightly clumsily organized filament of vorticity. Now, with that comes some interesting dynamics, because westerner disturbances are baroclinic. Tropical depressions are primarily barotropic, we think, and so they have very different looking theta E profiles. So when we look at the vertical cross section of that interaction, which I have on the right hand side here, the black lines show contours of theta E, equivalent potential temperature. And you can see as the two systems approach, they kind of munch together these contours of theta E, and you end up with this very strong frontal zone between the two that results in very heavy precipitation, because there's a lot of instability, you get inversion of theta E profiles, but also you get vortex stretching in the lower levels, which intensifies the tropical depression. So that's vortex mergers. The next type is dynamically perhaps a little bit more complicated and challenging to explain in 1 minute. This is the jet streak excitation. So here, a western disturbance, as the blue marker here, is embedded in the subtropical jet. That's the green barbs. And you can see, because it's got a strong western disturbance, it's resulted in this big trough in the jet, big cyclonic bend in the jet. Downstream of that, you get this strong intensification. So jet streak forms. And ageostrophic theory tells us that on the right-hand side of an entrance region to a jet streak, you get a region of large-scale ascent, which is what you see here in the grey contours. So this is a region of large-scale ascent associated with the jet streak. It just so happens that in September 1995, that jet streak invited a tropical depression into its region of ascent. So this is the red blob here, and it moves along the magenta track into this region of high ascent. Now, looking at the dynamics of that requires a little bit of complex analysis, but I'll take you through it very quickly. So this plot on the right shows it's a time-based diagram. So we move from left to right. We're moving forwards in time, and then it's a vertical cross section in time, as it were, taken at the centre of the low pressure system, at the centre of the tropical depression. The red contours show Q vector convergence. So they're essentially a marker of where the jet streak is having a significant dynamical impact. And where those contours are solid, that's big ascent, and where the contours are negative, that's big descent, basically. And you can see that the black contours here, which are vorticity, as the tropical depression enters this region, which is associated with the jet streak, the vorticity starts to climb, and suddenly there's this big spike in vertical velocity. So the vortex intensifies, the tropical depression intensifies, gets very deep convection associated with it, and very heavy rainfall falls as a result. So that's the second type of interaction, that's jet streaks. The third is a little more simple. It's simply a moisture exchange. So tropical depressions, again here in the orange, can pass moisture, this is vertically integrated moisture flux, these black arrows, towards the environment of a western disturbance. That's again given in magenta here. You can see as that happens, often this is associated with very heavy rainfall. Now, in the panels below, I show this in terms of ascent, that's the grey contours, and vertically integrated moisture flux convergence, that's the coloured contours. And you can see as the western disturbance approaches here, it's entering this region of vertically integrated moisture flux convergence, and very heavy rainfall falls as a result. We can test this hypothesis by looking at moisture flux back trajectories. So here is 100 or so parcels released from the box of heavy rainfall. You can see all of these trajectories, no matter whether you release them from the lower troposphere at 800 hectopascals or the upper troposphere or mid-troposphere at 500 hectopascals, they all come from the tropical depression, but they're all lifted by the dynamics associated with the western disturbance.
That's a 2-minute warning.
Yeah. So the final type of interaction is the reverse of that, basically. So western disturbances can also provide moisture to tropical depressions. Now, western disturbances are extratropical. They inhabit the upper troposphere. They're associated with a lot less moisture. They carry a lot less moisture, but they still carry some moisture, and they could also, as in this case, modulate the monsoonal flow. So this is during the early part of a monsoon withdrawal, 2003. Here's a tropical depression coming in. Here's a western disturbance. You can see the western disturbance provides a very small amount of moisture flux. Again, we can confirm this with moisture flux back trajectories. So you can see associated with the low pressure system here, entering this big red box where the, I do hope you can see my mouse, by the way, entering this region of heavy rainfall associated with the low pressure system. Most of the moisture coming in is brought by the low pressure system itself, but about 15% in this case comes from the western disturbance with the associated increase in precipitation. So summarizing, there are 4 different kinds of interaction. We have the vortex merger, where the tropical depression passes underneath the western disturbance. Vortex stretching occurs and they end up as a single filament. We also have the jet streak excitation, so that's where a western disturbance triggers a jet streak, large-scale ascent downstream, which a tropical depression enters, and again intensifies, associated with very deep convection. And we also have the 2 different types of moisture exchange from tropical depressions to western disturbances, and rarely and weakly vice versa. Thank you.
Excellent. Thank you very much. I think we have time for a question, and Sachin has posted one in the chat. I don't know if you'd like to read it out yourself. Otherwise, I can do it. So, how does this interaction between depression and a western disturbance influence their lifetime?
Well, I mean, it tends to kill one or the other because you can't have both moving together, I suppose. Typically, we find that you can have cases where there's a sort of fleeting interaction. So a western disturbance may be too far north for any kind of dynamical interaction, but it may be briefly intensified through baroclinic interaction with the orography, which can be itself intensified by flux added into that region, moisture flux added into that region by the tropical depression. But these are the great unknowns at the moment. I mean, I've only really got these cases so far, and we need further investigation for that sort of information.
Excellent. Okay. Thank you very much. If there's any other question, please ask it now. If not, feel free to write a comment in the chat or write to Kieran directly. And if Dr. Ambrogio Volonte could open up his talk, please, and share it to the world.
Yes,
So
I'll
all
share
of us
it.
that are here watching.
I'll share it in a moment. Is it sharing?
Not yet.
Oh, so I didn't click. Let me go again. Yes.
Here it comes. Yeah, and just full screen, please.
Screen. Let's go full screen, and let me.
Excellent. Yeah.
Use my laser pointer. Okay.
Okay. Thank you.
So shall I start?
Yes, please.
Good. Yeah. Okay. So this talk is about as the title says, the interaction between tropical and extratropical air masses controlling the progression of the East Asian summer monsoon. So just a brief introduction. This is an analysis of the East Asian summer monsoon progression, which focuses on the dynamics of the front and the interaction between tropical and extratropical air masses that converge at that front. We have we focus additionally, well, in particular, on the Mayu stage, in which we see like the bulk of the progression of the monsoon front, and which is also characterized by an especially pronounced air mass interaction and a especially clear frontal rain band. I'm using ERA 5 data, a 40-year climatology, and all the figures are from a paper that is, well, we hope, but we're quite confident, close to be accepted because it's gone through two rounds of review already, and we're almost there. So all the figures are coming from there unless it's specified. So we said that we're focusing particularly on the front. How did we detect the front? We developed and adapt a frontal algorithm that is based on the full horizontal gradient of θ of equivalent potential temperature at 850, so in the low levels. And you can see here for the climatology and the location of the front decade by decade, so for each 10-day period from the beginning of April to the end of July. And you can see that between April and the beginning of June, even mid-June, the progression is very slow, and then it speeds up substantially, almost 2 degrees per decade. during the end of June, which is the May period, and then July. We can now look at the different stages of the East Asian monsoon progression by also centering our analysis on the front. Here we have the widely recognized 4 stages of the monsoon progression, and we can see that in particular during the May stage we have this clear frontal band, whereas in the previous stages the rain is widespread over the southern side of the front, so it's mainly warm sector rain, and in midsummer all the structure is kind of weakening. So let's focus on the Mayu. In the paper you can see also an analysis of the other stages, but I'm conscious of the timings. And so we said that we see this frontal band. I'm sure you appreciate it's quite clear here. And looking at the regional circulation in the area, we can see that we have a climatological trough over East Asia to the north of the front. And also there is this high pressure over the Pacific, which is called, that's called the West North Pacific Subtropical High. So this terrible acronym, which also helps to steer the tropical flow towards the north as it's flowing, of course, anticyclonically around the high. So we have flow coming from tropical and even equatorial latitudes going towards the front, and is steered also by the North Pacific Subtropical High. If we look at the jet, Kieran in the previous talk has already mentioned the right entrance of the jet streak as being a preferred location for ascent, and this is exactly where we are with the Mayu front is in the right entrance region of this jet streak. So if we see the upper level horizontal wind divergence, we can see that it's positive, so it's divergence aloft, convergence at the bottom, so it's ascent. And also we can see that the frontal deformation of the front is maximum in this area. So the regional, large-scale flow is really conducive for the formation and of the front here. Now, let's focus more on what we see at lower mid levels and the different air masses. And I hope you can see my point here. So panel A, we can see the integrated vapor transport in the shadings, which is maximum towards the front and then along the front with the flow flowing around around the Pacific High. And if you see also the contours, this is integrated water vapor. And we can see that we have value above 50 kilogram per meter squared, close to the front. So we're around 30 degrees north. And these values are close to what we see in the Bay of Bengal. So if we were to label this air mass in terms of this water vapor content, this is really monsoonal in the sense of South Asian monsoon. It's got quite a lot of moisture in it. And also we can look at cross-section on this transect, so from the South China Sea to north of the Korean Peninsula. And you can see the maximum of the moisture flux being very close to the surface. So this is the southerly advection of tropical air. These red lines show equivalent potential temperature. So you can see warm air on this side, cold air on this side. This is the front. The magenta cross is showing where the front is. And you can see that the core of the cool air is slightly more elevated, is around 700 hectopascal. And this is just, well, we have the jet just on top of it, as you would expect. We also ran Lagrangian trajectories starting from the frontal location. We went back for 7 days, and the starting points represent the maximum and minimum theta points in the low level, so between 700 and 900 hectopascal in this area. And you can see that the core of the warm airstream is coming all the way from the equatorial Indian Ocean. At least this is the path that it goes through that travels in 7 days, whereas the cool airstream is coming from Central Asia and traveling on the northern side of the Tibetan Plateau. You can see that the two airstreams, this is the cool one, this is the warm one, they travel at different heights and they have a very different moisture content, with the moisture content of the warm one being quite constant all the way from the equatorial Indian Ocean to over China. So now we also looked at interannual variability of like this setting during the Mayu stage, looking at two subsets containing the 10 years with highest latitude and lowest latitude of the front at the end of June, which is a climatological time of the Mayu. And we can see that, as per definition, there is a difference in the latitude of the front, but in the low latitude here, the rain band is narrower and more intense, and also like these low latitude years are characterized by a more intrusive cool airstream. You can see the difference in the 325 Kelvin theta ray line. I'm very quickly moving to this one.
That's a 2-minute warning.
Yes, we're on track, I think. The low latitudes here are accompanied by a southward displaced Pacific subtropical high and a more pronounced upper level trough. And we can see also some differences in the trajectories with warm air originating further down in the tropics, and like cool air, again, even at low, when the front is at lower latitudes, is coming from mid-latitude Central Asia. So just a summary, we developed this front detection algorithm, and we used to identify the East Asian summer monsoon front. We highlighted the clear role of the subtropical westerly jet, you can see the schematic here, and the Pacific subtropical high in driving the evolution, like in steering the airflows and in anchoring the front. The interaction between tropical and subtropical air masses converging at the front is especially pronounced during Mayu, and we showed this looking at the trajectories. And we showed that also, I did this very quickly, but you can look at the paper. I mean, the preprint is available and the paper will be accepted soon. So you can look at the paper that the jet and the Pacific high really play a role in the variability of the front northward migration. And finally, I mean, this framework, we hope that will be used for like plenty of different activities. For example, looking at extreme events, performing model evaluation, looking at model prediction and projections. And for extreme events, this is an example from a study that we published in the special issue of AAS on the China 2020 floods. This is this event was characterized by the front stalling in this area for more than a month, not progressing north. And this is the 5 days period with the most intense rainfall. We see a wide area with more than 400 millimeters in 5 days. And this was characterized by this northerly displaced subtropical high, a stronger trough. You can see a very strong ascent, and you can see that to finish that the cool trajectories now are really coming from high latitude. So the contrast between tropical air and extratropical air is quite severe in this case. And with this, we finish, and thank you for the attention.
Great, thank you very much, Ambrogio. Does anyone have a question, either from WebEx or from YouTube for Ambrogio? Please put up your hand or just ask it directly. I mean, I was just going to say, do you think there's potential to really open up the kind of Lagranto code and make it something that anyone can use to do this type of analysis on the air masses and you know, interface between tropical and extratropical air masses and so on?
Well, I think that keeping aside the technicalities of Lagrange, because some people can use like other models or like other software, or can use Lagrange and adapt it to whatever model they're using, whatever data. I think there's a lot of potential. There's a big scope to do this air mass analysis on monsoon and tropical extratropical interactions, and yeah, like we did. Yes, absolutely.
Great, thank you very much. Okay, if anyone has any questions for Ambrogio, then please feel free to write them in the chat of either YouTube or WebEx, and we can follow that up later. So now we'll move on to the fourth scheduled talk in the session, which is again given by Dr. Kieran Hunt on the modes of coastal precipitation.
I'm back.
You're back again. There you are. Excellent. Thank you.
I'll share it properly this time.
Yeah. Yep, there it is. And full screen it, please. Thanks. Please go ahead.
Cool. So this is the second talk, same project, but very different region. So this is looking at coastal precipitation over the Western Ghats and how we can understand modes of variability embedded within that. So this work was motivated by predominantly work done by Jennifer Fletcher off the back of the Encompass project. You can see that on this left-hand panel here. And she found that during a period in 2016, where we had an intensive field campaign in this region with some flights, there was a period of intense rainfall off the coast, which you can see here, and that was followed by a period of intense rainfall over the coast, so over land. Basically, this is a cross-section through India, like a Hoffman through India, if you like. A similar result was reported by Zhang and Smith about the same time, that they looked at a much older case in 2008. And again, you can see here there's a period of predominantly offshore rainfall, and then that just transitions into this very tight band of coastal rainfall that's also quite intense here. And similar results found by Shige et al. They found variability existed on whether the rain was onshore or offshore, and it looked to them like the BSISO might have a role to play in that, which they put down to local vorticity and wind. But these are mostly case studies, and we want to do things climatologically, so we can throw the big statistical engine at them. And so to do that, I've drawn a box around the region of interest here, which has got the Western Ghats in the middle, and then a big chunk of the Arabian Sea, and some inland area of Karnataka as well, and a bit of North Kerala. And the red dots indicate local radiosonde stations, which will be useful later. So over this box, I've taken trim rainfall. I've done a low pass on it to get rid of the diurnal cycle, so 48-hour low pass on that. And then just throw standard EOF analysis at it. And the first EOF that pops out is this one, which just describes the magnitude of the mean rainfall of the region. So not very interesting. But the second EOF that comes out is this nice dipole, where in one mode you've got heavy rainfall over the coast, tightly bound to the coast, and a rainfall deficit over the ocean, and with opposite sign, a region of broad rainfall over the ocean and a deficit over the coast. And that mode explains about 14% of the total precipitation variability in that region, which is quite useful. So we do a little bit of a sanity check on that, make sure that that EOF, that PC principal component, describes what we think it does. So we can kind of put the PC2, this is, back in and create this kind of pseudo Hoff-Muller diagram here. So this is rainfall as a function of longitude and PC2, and you can see when PC2 is very negative, rainfall is very heavy offshore. As we increase PC2, the offshore mode weakens, then drifts onshore, and then at very high PC2, we have very strong rainfall associated with the coast, dry region over the ocean. We can see that for the Fletcher transition, here, the PC2 jumps from a value of near -4 up to a value of about 2.5, so that's good. We seem to have captured that, which is what we wanted to get after all. And also, just as a final sanity check, we can compare the values of PC1 and PC2. So that's the PC that describes the magnitude and PC that describes the dipole. We compare that to box mean precipitation, where PC1 does very well, correlation 0.98, and simple rain over land minus rain over the ocean measurement. And again, PC2 does quite well on that. So that's good. Now we can move on and look at these things in a bit more of a composite way. But first, let's just have a quick aside and look at how our models capture the Fletcher transition, now that we have a way of describing the regime change. So you have here a phase space that has PC1, the magnitude of the rainfall over the whole region on the y-axis, and then the x-axis describes PC2, which is the offshore versus onshore or coastal mode. And so the Fletcher transition here in black, this is for trim. You can see it starts offshore and then it meanders and then it goes onshore, and PC2 increases. We look at it in CMORPH, we have very similar morphology of the regime change, but just the magnitude of precipitation is a little higher. Now, when we look at this in versions of the which is the Met Office's operational model, we ran some experiments for this area for this time period as part of Encompass. With 17-kilometer model where convection is parameterized, it doesn't do very well. It doesn't capture the rainfall over the ocean. It's kind of stuck to the land. And we can see that in the Hofmüller down here. The storms are stuck to the coastline. They don't go anywhere. There's no real movement. When we add explicit convection in by strengthening the resolution, increasing the resolution 4.4 kilometers, we find that transition is captured. And it gets better and better as we increase the resolution through 1.5 kilometers. So on to a little bit of what's going on in these transitions. What controls, onshore versus offshore? Firstly, we have a little look at the structure. So this is using trim precipitation radar overpasses, and this is the fraction of overpasses in offshore cases. That's where PC2 is less than minus 1.5, and onshore cases where PC2 is greater than 1.5. And you can see that basically we get convection over a broad area during the offshore cases and over the Bay of Bengal as well, but nothing really over the land. And then during the onshore cases, we get nice deep convection over the land. There's not any difference necessarily in the strength of that convection. It's just the area that it covers. So what's causing the difference? Well, we can dig into some reanalysis and figure that out. So here I've taken a composite onshore minus a composite offshore set of variables. In this plot on the left here, the orange contours show low-level vorticity, the black arrows show vertically integrated moisture flux, and then the blue and red show the difference in rainfall, and the green dots show the locations of radio sun stations, which will be important in a minute. And what you see is basically during the onshore regime, you associated with comparatively much stronger monsoon trough, and as a result of that, much stronger westerlies impinging on the Western Ghats, bringing more moisture in. But that story is not complete. When we look at this in the vertical, we also see that the onshore regime is associated with a big dry intrusion in the mid-troposphere over the ocean. That means as convection moves in off the ocean and it tries to deepen, it ends up entraining this dry air and is essentially capped. It can't get any deeper, so the rainfall's not very heavy, and the storms have the chance to then propagate over land and continue raining there. And we notice when we look at this purely statistically driven composite that it looks strikingly similar to the schematic proposed in the Fletcher paper. Down here you can see the dry intrusion capping the rainfall and then a big storm over land associated with more a moisture surplus in the upper troposphere. So that's good. I mean, it seems like we've kind of captured the broad synoptic mechanisms that describe this. We can see this dry intrusion a little bit more by using actual radiosonde observations. So these are 3 stations, one in IMS-Delhi, that's over the Arabian Sea, one in Mangalore, that's on the coast, right on the coast, pretty much on the beach, and then one in Bangalore, that's much further inland. So that's these 3 dots here. This is IMS-Delhi here, this is Mangalore on the coast, and then Bangalore is inland. You can see that when we compare the onshore and offshore regimes, so that's the blue, black, and red, respectively, with black being a neutral regime, that there's no real change in the Cape. The temperature profiles are very similar in each case. There's not really a statistically significant difference there. What does change is the moisture. We'll find that over the ocean during an offshore regime, the troposphere is much moister at the lower levels. But as we move close to the coast, there is this inversion. So the upper troposphere is very dry, and during an offshore regime, and during an onshore regime, the upper troposphere is very wet, and that allows these storms to develop as they move inland, which is why you see the profile over Bangalore that you do, where during an onshore case, the upper troposphere is much moister. So I think I conveyed what I intended to there.
That's a 2-minute warning.
Yeah, that's fine. By my count, it should be about a 45-second warning, actually. So we look at the roles of intraseasonal variability in this as well, what we have 2 proposed routes for that. So one is the BSISO, which the Shige paper at the beginning looked into. And we can look at very strong cases of onshore and offshore regime, very, very strong cases, so PC2 having a value of less than -3 or greater than 3. And we plot those on a Wheeler-Hendon type diagram for the BSISO. You find that phases 3 and 4 are strongly associated with offshore, phases 5 and 6 strongly associated with onshore. But there is noise as well. It's not a complete description, but it describes a lot of it. And a lot of the rest is described by LPSs. So here we take the LPS track catalogue from my first talk. We bin the tracks into these 1-degree boxes, and they take the average value of PC2 when there's an LPS in that box. And you can see that when an LPS is in the middle of the trough, the value of PC2 is very high. That's because the trough is strengthened, the westerlies are increased, there's a lot more moisture impinging on the GATs. When an LPS is in an unusual position, southern edge of the trough or the northern edge of the trough is disrupted, breaks down. As a result, its westerlies aren't there. You end up with no dry intrusion coming down, and as a result, there's increased convection over the ocean. So there are the summary points. We use an EOF analysis to draw out these onshore and offshore regimes. Cape is not important. Mid-tropospheric humidity is important, and both the BSISO and LPSs can describe this on an intraseasonal basis. And this paper is published at this link here. Thank you.
Excellent. Thank you very much, Kieran, for your second talk and for keeping to time. There is a question that Sachin has just put into the chat. Any depression forming in the Bay of Bengal will have an impact on rain over the GATs, or is it more region specific, such as southern versus northern? I guess that's depression in the Bay of Bengal.
Well, I guess any LPS will affect the large scale dynamics. And you can see it quite, I guess, here. If you have one at the edge of the trough, at the eastern edge of the trough here, where it's supposed to be, if you like, then it enhances the trough, and as a result, the overall westerly circulation impinging on the GATs is increased. But further south, those dynamics are affected a bit differently, and in fact, you can actually end up inducing anomalous easterlies if an LPS is far enough south, which really drives rainfall over the ocean.
Excellent. Thank you very much. I don't see any other questions in the chat on YouTube. So if anyone does have any further questions, please post them in the chat or send an email directly to Kieran. So we move on to the 5th talk of the session, which is given by Dr. Venugopal Thalam on quantifying the role of antecedent southwestern Indian Ocean capacitance on the variability of summer monsoon rainfall over homogeneous regions of India. So if Dr. Venugopal could share your screen now, that would be great. And I will give you a warning after 8 minutes of the talk. Yeah, and you just need to full screen. Excellent. Okay, you can go ahead now. Thank you.
Thank you, Andy. Yes. So I'm going to talk about the role of antecedent southwestern Indian Ocean capacitance on the variability of summer monsoon rainfall for homogeneous regions of India. So you can see the list of authors who has contributed to this work, and this work is currently under review. On the left, you can see that the monsoon structure, the southwest monsoon structure, and it is basically a large sea breeze coming from the southwestern Indian Ocean. So our focus was our focus is to look at how the southwestern Indian Ocean ocean parameters could influence the total monsoon rainfall over India. So basically, it is a statistical study. So on the right, you can see that different homogeneous regions we have considered for this analysis. So this is the total monsoon. The contour or colors here are the monsoon rainfall patterns in a millimeter per day, and in total it is around 890 millimeter per season. So I would like to start with the caution here. The monsoon and cyclones are mostly a couple phenomena and mainly controlled by the atmosphere. So having said this, so monsoon predictions. So there are many projects which are focusing on the monsoon accurate and advanced monsoon predictions, ranging from diurnal to monthly and seasonal, and maybe annual predictions as well. And we usually do statistical and dynamical and numerical models for monsoon predictions. But most of the models which are in use are focusing on the atmospheric parameters, and only SST is the ocean parameters going into the models. So our aim is to see what is the upper ocean role in the monsoon forecasting. If you could include upper ocean parameters in the monsoon forecasting, how's the forecasting lead time or the accuracy will improve. So for that, we want to test with the SST as well as the upper ocean parameters such as ocean heat content and ocean mean temperatures. So to start with the background here, so this is the study we published in 2015. So basically, I think you can see my pointer. Okay. So basically, the IMD takes box B here for the seasonal forecasting of monsoon. The SST in the box B here. So this is from January to September. So whereas we attempted to correlate Indian summer monsoon rainfall with ocean mean temperature in the box you see here. So we found a good relationship with ocean mean temperature in the box A in all months from January to September. And whereas if you see the SST correlations, they're a bit lesser than the OMT ocean mean temperature correlations. Overall, we found a good correlation between ocean mean temperature and Indian summer monsoon rainfall in January and February. And whereas the SST in box A shows good correlations, but with less significance. So OMT, with OMT, we can further reduce the we can further increase the lead time from February, March to January and February here. So this is another study where we focused on the percentage of deviations in the Indian summer monsoon rainfall and the percentage of deviations in the SST and ocean mean temperature over the southwestern Indian Ocean. So this is the annual seasonal percentage deviations from 1993 to 2017. So you see that the blue boxes here where the OMT percentage deviations are not matching well with the ISMR percentage deviations. Whereas these boxes here, pink boxes here, they are SST percentage deviations where they are not matching with the ISMR percentage deviations. So similarly, we also looked at the dipole mode index because the monsoon patterns and as well as the total monsoon rainfall is basically depends on the Indian Ocean dipole as well as the El Nino ENSO conditions. So we looked at the DMI index as well as the DMI index computed with the ocean mean temperature over those boxes. And similarly, we also looked at the El Nino Modoki index and the Nino 3.4 index and the ISMR percentage deviation variability with these two indices. So overall, we found a good correlation with the OMT percentage deviations. So if you see the average above average rainfalls, where in our study period we had 9 above average rainfall above average rainfall years. So in those above average rainfall years, so rate of success with the OMT percentage deviation was 78%, and the below average rainfalls among 16 below average rainfall years, so rate of success was 81%, whereas the SST-PD showed only 55% and 63% respectively. So overall, if you see the different parameters, how the different parameters are performing with the compared to OMT percentage deviations, so the OMT has a good correlation with or better performance than all other parameters, which is showing 80% success rate in the study period, followed by SST percentage deviations on the box we have chosen over the southwestern Indian Ocean. And yeah, so following this, we try to look at the how the homogeneous rainfall will vary with the SST and the mean sea level anomalies, which is a proxy to ocean heat content. So if you see here, there is significant changes in the monsoon rainfall during the study period from 1993 to 2019. So where the rainfall is decreasing in the regions like Ladakh and all, and the northeast parts of India. And similarly, if you see the SST here, SST has been increasing, and sea level anomalies also on the positive side. And the mean sea level anomalies and SST has good correlation prior to the monsoon onset. That is during April and May. So we tried to switch different months and found the similar correlations between these two parameters. So we tried to we computed standardized monsoon rainfall. So we divided deficit years as standardized rainfall less than minus 0.8 and excess monsoon years as standardized deviation as if standardized deviation is greater than 0.8. So, and we try to remove the Nino 3.4 from remove the impact of Nino 3.4 on the SSTA and IMS-Delhi using this particular approach. So this is the composite of excess.
That's the 2-minute warning, please.
Yeah, thank you. So this is the composite of excess and deficit monsoon years and the normal monsoon years. So you see that there is positive SST anomalies and the strong winds during the excess monsoon periods, and the and is opposite in the deficit monsoon years, and the winds and the SSTA are normal during the normal monsoons, or moderate in the during normal monsoon years. And similarly, mean sea level anomalies also show similar signature. So with positive anomalies over the southwestern Indian Ocean, they show negative anomalies during the deficit years, and they are moderate on the normal ISMR years. So this is the correlation between SSTA and ISMR. So starting from the June previous year to the May, the current year. So we found strong correlations during the winter time, as you can see here. And so This is again a homodular plot. So averaging 40 to 65 degrees east and 10 south to 10 degrees north. These correlations, how the zonal and meridional correlations are varying here. Similarly, we did the similar analysis with the mean sea level anomalies. So these mean sea level anomalies correlations also showing positive higher correlations during the winter time. Yeah, and we have eastward propagation in the in these correlations. Yeah. So if you see the homogeneous regions, how the homogeneous rainfall correlations are with the SSTA and mean sea level anomalies. So we found that the correlations lie at 0.2 for the all India summer monsoon rainfall, and it is higher for the SSTA correlations are higher for the Central Indian rainfall. Yeah, sorry. And west so yeah, Northeast India and the western coast of India shows the higher correlations with the mean sea level rainfall, mean sea level anomalies. So yeah, these are the references. Thank you.
Excellent. Thank you very much. Does anyone have any questions for Dr. Venugopal? If so, please put up your hand. I can't see any in the YouTube channel either. Okay, so in the interest of time, we should move on to the final talk. Thank you very much for your presentation, Dr. Venugopal. Please feel free to continue asking questions in the chat. So now we move on to the sixth talk from the session, Dr. Subrata Kumar Das, who is going to talk about radar-derived properties of the convection during the passage of low-pressure systems. So if you could share your slides now, Dr. Das, that would be excellent, and move to full screen mode. Yeah, that should do it. Excellent.
Is it full screen?
Yes, it is. Thank you. You can start now. Thank you.
So, hello everyone, and good afternoon and good evening from India. I am Subrata Das from Indian Institute of Tropical Meteorology, IITM, and will be presenting the work radar-derived properties of convection during the passage of the low-pressure system. So the work is being contributed by Abhishek, Murli Krishna, and Vinita. So this is what is the background of this study. So I will just give a brief. So in the tropics, as we know that convective activity is one of the process that is influence the local and the large scale weather system. So the figure on the left, which is the figure A, shows the JJS mean OLR, which is the outgoing long wave radiation distribution, as OLR is considered as a proxy for the convection with the low OLR value representing the deep convection. So during the summer month, there is a widespread convective activity. You can see the lower values, which is in the red color, over the Indian subcontinent. So these widespread convections are embedded with a variety of the convective scale, ranging from the small scales cumulative to an ensemble of clusters, and finally organize themselves into the mesoscale convective system. So figure on the middle shows the JJS climatology of the LPS. So these black dot marks are the genesis point, which I have taken from the Mira et al.'s paper, and the contour lines are the frequencies of occurrence of the LPS. And this is from the Hurley and Booth dataset. So what we have observed, that most of the LPS are initiated in the Bay of Bengal and propagated westward toward the western rims of the monsoon trough. Okay, so those two things are the very well known. So now on the right hand side, we have shown the rainfall anomalies for the LPS days. So here you can see we have taken the seasonal mean and then subtracted the rainfall during the LPS day. So there is an elongated band of the positive rainfall anomaly along the trough, monsoon trough, indicate that this area get the most of the seasonal rainfall during the LPS events. So these are the three well-known pictures. So we try to understand what type of the convective systems are dominant during this LPS episode. So for this, first we have to identify the LPS day. So we have taken the IMD annual monsoon report and categorized lows, depression, and deep depression. They have categorized. We have directly used those data sets. And for the convection, and to study the three-dimensional structure of the convection, we have used the TRIM precipitation radar data along with the ground-based S-band radar data over the Kolkata. So I will come why we have only use this Kolkata data. It will come in the subsequent slide. So first, just want to highlight that this TRIM will give the vertical information about the convection, and that we have divided into the 4 categories like deep convective core, WCC wide convective core, deep wide convective core, and broad stratiform. These are classification initially made by Romstek et al. So at a quick glance, I can say that DCCs are those where the radar echoes are intense more than 30 dBz and crossing the 8 kilometers. So you can define it as a young and vigorous convection. Wide convective cores are the same where the radar echoes means crossing the 30 dBz and the area is also greater than 800 kilometers. So this will be the intense echo with a widespread convection. And DWC will have both the property. That is, means radar echo will be more than 30 dBz. It will be deeper than 8 kilometer and covering 800 kilometers square. And broad stratiform means stratiform region having a widespread area of more than 800 kilometers, regardless of those intensity. So these will be, means we can say that these are very well developed MCS system. So this slide shows the spatial distributions of this BSR, broad stratiform, deep convective core, wide convective core, and DWC during the only the monsoon low episode. So what we have observed that BSR and this WCC echoes are most likely over the Myanmar coast only during the low episode, and this DCC and DWC are mostly observed along the Himalayan foothills. So we can say that during the low, the rainfall, what we have observing over the trough regions are mainly associated with the BSR and DCC and DWC. So this is for the same spatial plot, but for the depression cases. So what we have observed over the North Bay of Bengal, and there is a higher frequency of DCC, relatively higher, and DWC, indicating this LPS Genesis region, because in the first slide we have seen that these are the LPS Genesis region will have the convective rain, and there is an increase in the BSR over the core monsoon zone, which is the central India, which is indicating that MCS structure is contributing to the rainfall variability over this region during the depression period. So this is again the spatial plot for the deep depression cases. So here, interestingly, we can see that the BSR storms are higher over the central India region, and the DCC, which represents the young and the vigorous convection, and the DWC, which shows that extremely intense and the organized convection from their definition. So therefore, it can be concluded that this maximum LPS occurrence frequency region lead to this deep and widespread organized convection, and the BSR observed over the central India region. The southwest core of this LPS genesis come from the trailing or outflow of the mature, well-developed MCS, because we have seen that there are more BSR during the lows over the Myanmar coast. So this is also from the TRIM data set because I forgot to mention, because TRIM data sets we can use it to study the large scale convective system. So here we are showing the CFAD, which is a control frequency by altitude diagram, to understand the vertical structure of the convection by considering their genesis box. So I have just considered the area where there is an LPS genesis by considering the 17 to 23 and 80 to 90 degrees. So here what we can see that both warm and cold rain process are evident during the lows and the depression. This is for lows, depression, and the deep depression. And the deep depression has a well-marked maxima above the melting layer, which is roughly a 5 kilometers, suggesting the dominance of the deep convective system. So this is over the LPS genesis region, and this is over the core monsoon zone, the CFAD. Core monsoon zone means the central India region. So during the low episodes, the CFAD shows the narrow structure, means width of the maximum occurrence, indicating the convective nature of the storms, because there we are observed the DCC were dominant. Okay, and during the depressions and the deep depression cases have the core of the maximum frequency for the dominance of the stratiform process, where the broad stratiforms were observed, and there is a bimodal distribution in the deep depression cases. So this is the rainfall contribution for the lows, depressions, and the deep depression cases. So here we have taken the standardized anomaly. So this is a standardized anomaly which shows that less than 1 means it has least significant. So you can see that in lows cases, it's a least contributor to the monsoon rainfall, but for the depression and the deep depression cases, it is contributing to the total accumulation. So to study the storm scale convection, we have used the Kolkata S-band radar. So here, this is the Kolkata radar location. This red color indicates this radar domain. So here, what you can see, because here, if you see, there will be the coastline. So I have not shown a overplot here. So most of these storms during the LPS days are the deeper and the intense, because this is a ecotop height, 35 degrees ecotop height. And here for the composite radar domain, you can see that LPS are having the higher 35 dBz ecotop height as compared to the JGS mean. So now we try to find out these extreme cases, whether means extreme rainfall cases over the radar domain. So what we have done, so radar domain average rainfall accumulation, and then we have find out the 99 percentile of this rainfall value over the central India, which is exceeding. We define it as an extreme case. So if there is an extreme cases, so our radar shows that they are the more deeper, and this is the percentage volume greater than 40 dBz. So those are the more intense. This is the standardized OLR anomaly for the high precipitating event. So here you can see that this is mostly confined in this area. So LPS is good for the seasonal accumulation rain in the larger picture, but if you consider this local area, it precipitates very heavily, especially over the inland region. So with that, I can conclude that the synoptic scale convective systems are the major rain-bearing system in the core monsoon region, and the monsoon lows contribute least to the seasonal mean. But the depressions and the deep depressions are the major rain-producing systems, and they vary from the large spatio-temporal scale, from the storm scales to the MCS scale. And so this we can in the future, actually, since we have used only the one radar data, so we want to use some more radar data set from the IMD over the monsoon trough region and try to hypothesize our findings. And other thing, we try to see the contribution of dynamic and thermodynamic control on the extreme precipitation event on the sub MCS scale triggered by the LPS by using these moisture budget equations. So thank you.
Thank you very much. Thank you very much for that really interesting talk. Yeah, I'll certainly watch that again because I think there's a lot of interesting stuff that's relevant to our work in that. I see that Kieran has put a question in the chat. Would you like to ask it?
So I'm trying to open this. I don't know how to go this.
Well, I was just going to say if Kieran would like to ask it directly, otherwise I can read it out for you.
No, means I can see.
It says it looks like deep depressions were associated with weaker rainfall than normal depressions. Any idea why that is?
Yeah, so this is for the standardized, I think, rainfall anomaly he's talking about. So we have used this Aphrodite data to see, because radar derived rain we cannot compare with this Aphrodite data. So we have to really look, means that is I also saw this one, deep depressions standardized rainfall anomaly is quite less, but depression cases we are getting the more. So we really have to look in that one.
Excellent. Thank you very much for that response. There are no questions that I can see in the YouTube channel. Does anyone have a further question here?
Oh,
It doesn't look like it, so that's fine. Thank you very much once again. So I don't think we have Dr. Kulkarni able to give that first talk that was missed, and it looks like we're finishing right about on time. So thank you very much to all of the speakers for presenting your work today. I encourage you to advertise the YouTube links on your social media channels so that other people can watch the talks again. And does Dr. Patnaik have any final message?
Thank you so nicely conducted. We are in time. Of course, we missed one talk, but anyway, we are in time. So I think it was very wonderful. I was listening to the talk, so I didn't ask any questions, but I was listening. Many good talks were there. So thank you, Dr. Andy, for for doing your job from all fronts, speaker invited me, and also the chairing the session. So thank you very much, and also I thank all the speakers.
Great, thank you very much.
So tomorrow morning again we will have in Hall A, start with the 4 invited talks at the local at 8:30 Indian time and 3 UTC. Okay, see you tomorrow again.
Thank you very much. Good evening, everyone.
Good evening.
yeah, thank you.